The history of special relativity consists of many theoretical results and empirical findings obtained by Albert A. Michelson, Hendrik Lorentz, Henri Poincaré and others. It culminated in the theory of special relativity proposed by Albert Einstein and subsequent work of Max Planck, Hermann Minkovski and others. Introduction. Although Isaac Newton based his physics on absolute time and space, he also adhered to the principle of relativity of Galileo Galilei. This can be stated as far as the laws of mechanics are concerned, all observers in inertial motion are equally privileged, and no preferred state of motion can be attributed to any particular inertial observer. However, as to electromagnetic theory and electrodynamics, during the 19th century the wave theory of light as a disturbance of a light medium, or luminiferous ether was widely accepted, the theory reaching its most developed form in the work of James Clerk Maxwell. According to Maxwell's theory, all optical and electrical phenomena propagate through that medium, which suggested that it should be possible to experimentally determine motion relative to the ether. The failure of any known experiment to detect motion through the ether led Hendrik Lorentz, starting in 1892, to develop a theory of electrodynamics based on an immobile luminiferous ether, physical length contraction, and a local time, in which Maxwell's equations retain their form in all inertial frames of reference. Working with Lorentz's ether theory, Henri Poincaré, having earlier proposed the relativity principle as a general law of nature, used this principle in 1905 to correct Lorentz's preliminary transformation formulas, resulting in an exact set of equations that are now called the Lorentz transformations. A little later in the same year Albert Einstein published his original paper on special relativity in which, again based on the relativity principle, he independently derived and radically reinterpreted the Lorentz transformations by changing the fundamental definitions of space and time intervals, while abandoning the absolute simultaneity of Galilean kinematics, thus avoiding the need for any reference to a luminiferous ether in classical electrodynamics. Subsequent work of Hermann Minkovski, in which he introduced a four-dimensional geometric space-time model for Einstein's version of special relativity, paved the way for Einstein's later development of his general theory of relativity and laid the foundations of relativistic field theories.